Here, at the very bottom of the canyon, we have stable nuclei, present in nature every day. It's the red ones. On the other hand, the steep walls of the canyon are unstable nuclei. The ones on this side of the valley, they have more neutrons than necessary for their stability. And on this side, they don't have enough of them.
Does this mean that only stable nuclei exist in nature on a daily basis, and the unstable ones, even if they arise, it's only for a moment, after which they will turn into stable ones?
Some unstable nuclei are present in nature around us. After all, Maria Skłodowska-Curie discovered the unstable element radium in the natural uranium blend. Because admittedly, the heaviest elements are always unstable, but they decay slowly, sometimes over billions of years.
So, ever since they were created, that is, at least from the beginning of the formation of the Earth, they have not yet completely decayed. Now I understand why radioactive uranium was found even in the Polish Tatra mountains. Okay, you have said a few times that unstable nuclei change into other nuclei. How is this possible?
Don't think about unstable atomic nucleus like a nice bunch of protons and neutrons. Really, strange things happen there. An unstable nucleus can change into another one. It has decay in 3 ways. The first is fission. The second possible decay mode of unstable nuclei is when the nucleus ejects a group of 2 protons and 2 neutrons. We call this the emission of alpha particle, that is a helium-4 nucleus. But there are stranger transformations. For example, in an unstable nucleus that has relatively too many neutrons, a neutron may change its mind and become a proton.
Stars are made of an almost incomprehensible number of particles which gravity compresses into a super-dense core. This core is hot and dense enough to force atomic nuclei together, forming larger, heavier nuclei in a process known as fusion. The reverse process, where one atom splits into 2, is called fission. In both processes, the mass of the end products is slightly less than the mass of the initial atoms. But that lost mass doesn't disappear. It's converted to energy according to Einstein's famous equation. And since c² is such a massive number, both fission and fusion generate a lot of energy. In the most common pathway, 2 protons fuse to form a deuterium nucleus, which then fuses with another proton to form a helium-3 nucleus, which then fuses with another helium-3 nucleus to form a helium-4 nucleus.
This process is referred to as nuclear fission. So, a process in which heavy nuclei are bombarded with neutrons and split into 2 equal masses, releasing enormous amounts of energy, is called nuclear fission.
A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus, and is what determines, but not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are 3 types of decay: alpha decay, beta decay minus, or beta decay plus.
Classification of elementary particles. Elementary particles can be grouped into 2 broad categories, fermions and bosons, based on the property called spin, which is connected by the kind of statistics the particles are governed by. Almost all elementary particles spin about the axis, and its unit is h cross, where h cross is equal to h by 2 pi. Particles which have odd half integral spin are called fermions, and those which have integral spin are called bosons. These fermions obey Pauli's exclusion principle. That means no 2 identical fermions can occupy the same quantum states. Also, these fermions obey Fermi-Dirac statistics. The wave function which describes the fermions is antisymmetric. In the case of bosons, the bosons are not constrained by Pauli's exclusion principle. That means the number of bosons in any quantum state, in any given quantum state, is not restricted. These bosons obey Bose-Einstein statistics. The wave function of bosons is symmetric.
How do the positively charged protons in the nucleus stay together, since particles of the same charge repel each other? The answer is the strong nuclear force. There are 4 fundamental forces in the universe: the gravitational force, electromagnetic force, weak nuclear force, and strong nuclear force. Unlike gravity and electromagnetism, we can't directly observe the weak and strong nuclear forces in nature, since they're effective only at the subatomic scale. Let's compare the relative strength of the fundamental forces by assigning 1 to the force of gravity. We get this table. As you can see, the strong force is by far the strongest of the 4 fundamental forces, though its range is only about the width of the nucleus. When the protons in the nucleus approach each other more closely than a femtometer, that's 1,000 trillionth of a meter, the strong force becomes active and holds the protons together, since it's many times stronger than electromagnetism. So, atomic nuclei and atoms can be formed.
Dapat diketahui dan ditemukan fakta bahwa masih ada struktur yang lebih mendasar atau fundamental dari subpartikel seperti proton atau neutron itu sendiri yang disebut dengan quark. Quark sendiri sebenarnya telah diperkirakan keberadaannya pada 1961 oleh fisikawan Murray Gell-Mann tentang fakta kemungkinan adanya partikel yang lebih dasar dari proton dan neutron. Sebuah pengamatan pada hamburan inelastis yang dihasilkan ketika proton dibenturkan atau collider di akselerator partikel. Pengamatan tersebut menemukan pada hamburan inelastis mereka menyebut itu sebagai hadron, di mana hadron proton tersusun dari up quark atau quark naik dan 1 down quark atau quark turun yang diikat dengan gluon sang pembawa gaya, sedang neutron terdiri dari 2 down quark dan 1 up quark kebalikannya, juga diikat oleh gaya yang disebut dengan gluon. Quark sendiri terdiri dari 6 jenis, yaitu up atau naik, down atau turun, strength atau aneh, charm atau pesona, bottom atau bawah, dan top atau atas. Quark merupakan partikel paling dasar atau fundamental. Selain keluarga quark, keluarga lepton juga disebut sebagai partikel paling dasar. Dalam keluarga lepton terdiri dari 6 jenis, yakni elektron, neutrino, muon, muon neutrino, tau, dan tau neutrino.
A lepton is an elementary particle and one of the fundamental building blocks of matter in the standard model of particle physics. Leptons are a type of fermion, which means they obey Fermi-Dirac statistics and obey the Pauli exclusion principle. Leptons are characterized by several key properties. Spin. Leptons have a spin of 1/2, a fundamental property that contributes to their intrinsic angular momentum. Charge. Leptons have electric charge, and there are 2 types of leptons based on their charge: charged leptons and neutral leptons. Charged leptons. These are negatively charged leptons. The most familiar charged lepton is the electron. These are electrically neutral leptons, and the most well-known neutral lepton is the neutrino. Neutrinos come in 3 types: electron neutrino, muon neutrino, and tau neutrino. Leptons are unique in that they do not experience the strong nuclear force that binds quarks together to form protons and neutrons. They only interact via the electromagnetic force and the weak nuclear force, making them relatively non-interacting compared to other particles. Leptons play a crucial role in various particle interactions and are involved in processes such as beta decay, where a neutron transforms into a proton, emitting a beta particle, electron, and an antineutrino, a type of neutral lepton. The conservation of lepton number is an important principle in particle interactions, stating that the total number of leptons minus the total number of antileptons remains constant during certain interactions. Leptons, along with quarks, contribute to the diversity of matter in the universe and are essential components of the particle zoo described by the Standard Model.
If you've had any interest in physics at all, you've heard about a thing called the Higgs boson. But just what is it, and why is it interesting? In 1964, a physicist by the name of Peter Higgs took some ideas that were floating around at the time, added an insight or two of his own, and proposed that there was an energy field that permeated the entire universe. This energy field is now called the Higgs field. The reason he proposed this field was that nobody understood why some subatomic particles had a great deal of mass, while others had little and some had none at all. The energy field that Higgs proposed would interact with the subatomic particles and give them their mass. Very massive particles would interact a lot with the field, while massless particles wouldn't interact at all. The lightest of the familiar subatomic particles is the electron, while in the subatomic world, the king of mass is the top quark. It weighs about as much as an entire atom of gold, about 350,000 times more than the electron. I'd like to stress that we believe the top quark is not more massive because it's bigger. It's not. In fact, we believe that both the top quark and the electron are exactly the same size. Indeed, they both have zero size. The top quark is more massive than the electron simply because it interacts more with the Higgs field. Actually, if the Higgs field didn't exist, neither of these particles would have any mass at all. The Higgs boson is the smallest bit of the Higgs field. To understand how that works, we should again return to water. Everyone knows what water is. If you're immersed in it, you know that water is everywhere. It's a continuous medium, and there are no holes in it. We also know that water is made of molecules, specifically H2O. If you hold these two ideas in your head with the realization that water consists of countless individual molecules, you can now begin to appreciate the Higgs boson. The Higgs field that gives subatomic particles their mass is made of countless individual Higgs bosons, just like water is made of individual molecules. You should keep in mind that the Higgs boson hasn't been discovered yet, and what I'm describing is simply the most popular idea as to why subatomic particles have the masses that they do.